Welcome, I'm Mr. Kimball and this is your
Flipped Classroom. Lab procedure and write-up. I'm going to go through the list of things that we want you to copy down when you do the labs. We're going to do quite a few labs in this class, and we have a structured way to collect that information, and then we'll go into how to turn that information and analyze it into something useful and apply some implications. Okay, so what we have here is kind of a sample notebook section. So you'll start out, you'll title your lab, put the day's date that we're doing it, the objective. I will probably give it to you to start with, but then you're going to be expected to be able to come up with your own objective. What are we trying to get from this lab? The design. I will often have a sample set up, and then you will have to kind of copy that down and then reproduce that on your own. The procedure, we don't write that in our notebooks because typically that's what I'm giving you to begin with, and there's not a lot of sense in copying that down again. You'll find the procedure on Canvas, and that's where you'll open up the lab template. The data collection is going to be different for every activity or lab that we do, but you're going to want a table that's drawn with a ruler and neat and organized before you actually start doing your lab. So typically what you'll have on the right hand side is the dependent variable. That's the measurement that you're going to be collecting. You know, you'll use a ruler to get a dependent variable or a scale to get a dependent variable. The key here between independent and dependent is usually the dependent variable you're going to need a tool to get. The independent variable is going to be what you're changing. So whatever you decide to test or manipulate in an experiment, or if you're doing like a comparative study, it'll be the different things that you're comparing. And the dependent would be kind of like the criteria that you're comparing them in. So there's lots of different ways to do it. I understand that these terms, independent, dependent variable, are difficult concepts, but just keep in mind the dependent variable is something you're going to collect. You're going to have to use a tool to collect that data, and then the independent variable is going to be what you're changing, and you'll collect that in a table. Once you have that table, we're going to analyze it. Okay, so I've kind of like scrolled down on my page a little bit, and we're still on the same subject here, data analysis. I'm going to look at my table of data that I collected in the experiment, and I'm going to plot my dependent variable on the y-axis, and I'm going to have to use my units, and I'm going to put the independent variable on my x-axis, and I'm going to include units, and I'm going to make sure I include zeros in there as well. Tails. Okay. You've probably seen this in earlier grades. Alright, so tails, if you follow tails, you won't forget anything on your graph. Now the first thing is to draw your axes with enough room on your paper that you're going to be able to put numbers in here and a label with your dependent variable and your units. And so usually that means you're starting 1 to 2 inches inside the margin of your paper just so you have enough room. That's a big mistake a lot of people make. You're also going to need to include a title, so a descriptive analysis of the graph, whatever it is you're comparing typically. That'll be simple enough for us. You want to make sure you're labeling your axes, that you have your axes, that you're starting at 0, and then your intervals need to be the same. Okay, so and the intervals kind of go along with the scale. So depending on how big your data is, you want to choose an interval that you can display your data using about 80% of the graph. You don't want all of your plot down here and then you're going to draw this, and that's not very helpful. You don't want to have missing pieces of data that go off your graph. That's also not very helpful. So the rule of thumb is to try and plot your data using an interval that makes your data kind of fill about 80% of the graph. Okay, now that you have your data plotted, and I'm going to use my independent variable. I'm going to use length in meters, and I'm going to be measuring time in seconds. So if I think about a pendulum, I'm going to drop a pendulum of different lengths, and I'm going to try to measure the time interval or the period of that pendulum. I'm going to plot my data, and now I want to interpret. So if you remember, after your lab, we're not done. You've done labs in the past, and data analysis isn't it. This is figuring out what your data says. We also want to do what's called a CEI. We're going to do a conclusion, evaluation, and implication paragraph. Now, your conclusion is going to be the answer, right? And what trend or what rule did we see in our lab? The evaluation is going to be, do I trust that data? Is it good data? Did everything work out nice? Should I have done something differently? What would I change in the future? And then the implications is, what does that trend mean? How would I use that? Could I take that formula, that trend line, or that model that I discovered, could I take that and apply that to something else? And so in order to get to this, we need to do a few things here. The first thing that you're going to do is you're going to draw a trend line. Now you're going to take your straight edge and you're going to line up with the origin, and you're going to draw a straight line pretty much right through the middle of your data. Okay? You don't want to connect all the dots. So once you have your trend line, you need to pick cross points. So a cross point is somewhere on the graph that is very easy to line up with the numbers on your axes. Once you pick your cross points, you're going to do rise over run, which is really what that's saying is that's going to be a change in y over the change in x. Change in y is going to be, I think I'm running out of room, it's going to be y2 minus y1 divided by x2 minus x1. So on the x-axis, right, this is x2, this would be x1. On the y-axis, this would be y2, and this would be y1. And so you'd take those coordinates, your cross points here, and you're going to plug them into this formula, and that's going to generate a constant value for you. Okay? Now, this is a linear line, and so this takes the form of y equals mx plus b. B is the y-intercept, which is 0. M is the slope, which we just found, and that is k. And on my x-axis, I have length L, and on my y-axis, I have t time. And so what we did right here, this is your real world equation. This is the answer. This is your rule that you found, that you concluded. So after doing my data, after I did my experiment and collected my data and analyzed it, I discovered the model time is equal to some constant times L. Now obviously we're just making stuff up, that's not a true relationship, but this is a usable answer, okay? And then you would evaluate, was my data good, did I mess up, did I have outliers, did I have something out here I had to deal with, etc. Now implications, what does that mean? Well, that means if I had a length of a pendulum of a certain length, I could stick it in here and I could solve for a certain amount of time. So I could solve for the period given a certain length. Or I could predict the length. If I was making a clock and I needed my time period to be 1 second, I could predict the length of my hand in an old grandfather clock using this type of model. Okay. Now the real world equation is actually going to have a real value because you're going to have real numbers. In this case I just have k. Okay. But this is what's expected of you in a lab. So you're going to run through, you'll have a title, you're going to date it, you'll have the objective, you'll draw a design, you're going to find the procedure on Canvas, you don't need to copy it into your notebook, And then we'll collect data in an organized table using a ruler and a straight edge, and then you're going to interpret that data by changing it into a graph. You're going to go through this process of finding a real-world equation, and then you're going to kind of sum everything up in a conclusion, evaluation, and implication paragraph. So we're looking for maybe 4 or 5 sentences. Sometimes there will actually just be questions, so like post-lab questions, and that'll suffice, and you won't have to do a paragraph, we'll just answer the questions. Okay, proportions. There's 4 main base proportions that we'll use in physics: directly, inversely, quadratic, and root. So you're going to want to know these relationships between the formula and the line. It'll help in the labs as you plot your data and you see a scatter plot that might have a curve to it. It'll give you a better indication of what type of equation you're looking at. Now if I tried to put a line of best fit that's a line, it wouldn't fit the data as well as the pink one here, the quadratic line. And so quadratic formula is y equals kx squared. The root formula, which we don't see very often, is this logarithmic scale where things are still moving in the same direction. They're going forward, but they're going forward maybe at a slower and slower and slower rate. And so you have this slowdown as you progress through x. We often refer to the equation in y equals square root of kx, but when we graph it, it's going to be the y squared compared to x.